Moving right along, we're now at the top of page 7, and let's continue with this idea about the ground state versus a possible excited state. The ground state, there's only one for any particular element. This happens to be the ground state of aluminum. The way I know that is, and you can know that, is simply by adding up the electrons. So 2, 8, and 3 adds up to 13. 13 electrons in a neutral atom would mean 13 protons. So we're talking here about aluminum 13. And look up aluminum and you'll see that it says there 283. So that's the way the electrons are supposed to be when aluminum is unexcited or in the ground state. And then remember, an electron, any one of these electrons, can move to an orbit further away when it absorbs energy. So in order to get a possible excited state, and there are many, what you want to do is move only one electron, all right, from where it is to an orbit further away from the nucleus. And so in this case here, we start with 283, and if we move an electron, let's say, from the second orbit to the third orbit, we end up getting the numbers 274. And that would be a possible excited state. Now if I had started with 274, and you were asked, is this a ground or excited state? Again, you would add it up, 13, look up who number 13 is, and see that 283 is clearly a ground state. And since electrons in this case have moved further away from the nucleus, and what we're saying is to the right is further away from the nucleus, then that certainly is an excited state. And look, possibility, how about we take an electron from the third orbit and move an electron to a fourth orbit, or a distance further away. In that case, you'd get 2821. So we're always going to the right, away from the nucleus. But we're never going in the opposite direction, where we would get 373. This one, 184, what happened in this case was an electron jumped from the first orbit, all right, skipped the second orbit. So let's draw that here. And you ended up forming 184 as a possible excited state. Okay, so that's real easy. Now, let's contrast, or compare and contrast, better said, metals with nonmetals. That's what I have listed underneath here. And we can talk about ions and neutral atoms at the same time. All right, if you recall, metals lose electrons, forming positive ions. Metals are losers. Easy way to remember it, they're to the left of the step order in your periodic table. And so they are losers, L, they're losers, metal. Sodium, Na, metal, you're a loser. All right. And nonmetals, on the other hand, in their chemical reactions, gain electrons forming negative ions. You'll notice that if you look at the oxidation states of all the losers, the metals, they're all positive. While nonmetals, their most common oxidation states, the top numbers there, are negative. So sodium as an atom has the electron configuration 281. And sodium, if you look it up, which is element number, well, add it up. 2, 8, and 1 adds up to 11. So sodium is element number 11. There's its configuration in the ground state, and that's all we have listed here in the periodic table. If the sodium forms, as you can tell, a positive 1 ion, which is the only ion it can form, what that means is the sodium lost an electron. So it then becomes 2,8 because it loses its valence electron. So positive 1 means it lost the atom 1 electron to form that ion. And then on the opposite side, you have oxygen, which is a nonmetal. Element number 2 and 6 adds up to 8. There's its configuration. And being a nonmetal, non means opposite of metals, the oxygen is going to gain 2 electrons in forming an ion. So again, atom versus ion. In the case of sodium, atom versus ion. And for oxygen, the oxide ion, that -2 indicates that the atom gained 2 electrons to form that ion. Now that's a little confusing, why the loss of electrons would lead to a more positive charge, and the gain of electrons would lead to a more negative charge, starting from neutral. But if you recall that electrons are negatively charged, when you gain and lose negatives, everything is the opposite. And we'll follow up on that more and more in the bonding unit, and in particular in the redox unit. All right, the goal, if you recall, is to get 8 electrons in the last orbit, because 8 is the maximum. And the elements in the periodic table that start out with 8 electrons in their last orbit, if you recall, are in group 18. They're called the noble gases. We'll talk more about this in the next unit, of course, which is periodic table. But for now, understand, the whole goal of the elements is, through chemical reactions, to attain, to have a noble gas electron configuration. What that really means is, not that they turn into noble gases, that means they'll end up with 8 electrons in their outermost shell. And that is very stable. So let's write that right here. Very stable. Okay. That's an atom that is happy. All right, so again, metals are losers, forming positive ions. Non-metals are gainers, forming negative ions. And we'll practice this some more, of course, when we do bonding and when we do the redox unit. Again, the atomic concepts unit is real easy compared to the others, because you're making use of the table right there. The key is helping you so much to do so. Now let's continue on this page. Let me erase this here. Let's talk about my favorite, which is the Lewis dot structure. It's my favorite because the Lewis electron dot structure of an atom, and we'll talk about the dot structures of ions and molecules and all that in a second. The Lewis electron dot structure represents an atom with only its valence electrons. And so the maximum number of dots, or valence electrons, around any atom, if you recall, is 8. So why don't we see how we get these? And what I did here was I took the elements in the third row, beginning with sodium, or third period, better said, number 11, but its configuration, if you recall, is 281. You can look up sodium right now. And so it's only going to have 1 dot, 1 valence electron. The magnesium right next door is 282, 2 dots. Notice how I placed them together. And the way of getting a correct electron configuration is by placing the electrons beginning the first pair, the first 2 dots you should put together. So the first 2 dots together. I made it in bold, but we'll circle it to remind you. I call that the 12 o'clock position. So magnesium would have 2 at 12 o'clock, and if you wanted to, you could start at the 3 or 6. That's irrelevant, but you got to start somewhere. And then if we go to the next element, which is aluminum, all across the way, number 13, its configuration is 2, 8, 3. So it's got to have 3 dots. Now, choices, wrong choices that they might give you is aluminum like this, 1, 2, 3. All right, or aluminum like this, let's say, 1, 2, 3. That one's clearly wrong. All right. But I prefer, and you'll learn more about this later on in other courses, all right, in chemistry, I hope you take that, to keep those first 2 together. And so aluminum, with the first 2 together, 12 o'clock would give you this, and then what you do is you place electrons in the remaining, the other quadrants. You think of the aluminum as in the center of a tic-tac-toe. You're going to place electrons in the remaining quadrants, which is at 12 o'clock you start, then 3, 6, and 9. Even though on the Regents, technically, I'm sure your teachers are picky about this, but on the Regents, even if you did it this way, it would be okay. But I'm going to stick to something that will help you later on in the bonding unit. So I'm going to draw aluminum like this. And then, of course, you could have started at 6 o'clock, and then continue clockwise, place an electron in each of the remaining orbits, or each of the remaining quadrants, better said, if the element has more than 3 valence electrons. So, for example, if we go to sulfur here, sulfur's configuration is 2, 8, 6. And so sulfur, like oxygen for that matter, or any of the elements in group 16, has 6 valence electrons. So the way we worked that up is we did sulfur. We said 1, 2, 3, 4, 5, 6. In fact, if you did oxygen, it would be the same thing. Oxygen is just 2, 6. Right? And oxygen would be same number of valence electrons, 1, 2, 3, 4, 5, 6. And that's why oxygen and sulfur are so similar in their properties, because they have the same number of valence electrons. And that's for that reason, sulfur and oxygen and the rest of the elements in that column or group, in group 16, will behave similarly in their chemical reactions. All right. Then chlorine with 7 valence electrons, and then finally argon with 8 valence electrons. Argon has the maximum, which is an octet. Now, the difference between, again, an atom and an ion, if we're talking about the nonmetals, since we have nonmetals here, if you recall, oxygen, look it up, can form a -2 ion. We just said that a couple of minutes ago, just above in our notes. So that would mean that it would gain 2 more electrons. To show an oxygen ion, then, what you would do is you have the oxygen as before. There's the 6 as an atom, and with 2 more electrons it would have an octet. To show that it's an ion, we put a bracket around it, -2 charge. We'll do much more of this when we look at the bonding unit also. I think there's a question in this unit on ions, which is what we'll be doing after this page. All right, so the Lewis dot structure, the dots represent valence electrons. There's a certain manner in which you should fill these quadrants to get the correct electron dot structure. And otherwise, it's very easy to do. And finally, at the bottom of this page, we have 2 small points to make. One of them is on a very famous experiment which led to the nuclear structure of an atom. And it's the only experiment they really ask about, and that is Rutherford's gold foil experiment. And this diagram, in fact, comes from an old Regents exam. And what Rutherford did was he took some gold, which is very malleable, can be flattened into very, very thin sheets. And so it consists of a minimal number of atoms in thickness. All right, and this represents the gold atoms in this diagram. And what Rutherford did was he shot alpha particles at the gold foil. So it's the Rutherford gold foil experiment. Not aluminum foil, but gold foil. And these lines here represent alpha particles. So I'll use the Greek letter alpha to indicate that with a positive charge, because alpha particles, as we'll learn in the nuclear unit, are positively charged. So he shot these alpha particles at gold foil, And what he found out was he was able to detect them because the alpha particles are invisible to the naked eye. So he had some way of detecting these alpha particles as to where they ended up when he shot them at the gold. And what he found out was that most of the alpha particles went straight through. And that would be conclusion number one about this observation, was that an atom is one, mostly empty space. It was as if the gold wasn't there at all. All right. And secondly, Rutherford found that very rarely, but it did happen, an alpha particle would deflect back. And so what Rutherford proposed for this was the so-called nuclear structure of the atom. What he proposed was that, yes, an atom is mostly empty space, but every once in a while, the alpha particle struck a small, a tiny, but massive center, which he called the nucleus, and he took that term from biology. All right, so most of the, or all of the mass, because electrons are negligible, of an atom is central in the nucleus, and that's again where we find the protons and the neutrons. All right, so the nucleus is very small, but massive. Would be conclusion number two. And then he also found on the opposite side of the gold foil, some of the time the alpha particles were bent away from their original path, like this one right here and this one. And since Rutherford knew that the alpha particles were positively charged, what he proposed was that the alpha particles in this case, the ones that were bent away, were being repelled by the positive charge of the nucleus. So we'll draw the nucleus here as positive. So the three conclusions are: one, an atom is mostly empty space; two, the nucleus is very small but massive; and it's in third, it's positively charged. Up until that point, they used to think of atoms as these spheres that were just evenly distributed, the mass of the atom. But instead, because of the nucleus structure, Rutherford proposed, no, most of the mass, or all of the mass, I should say, is central, since electrons have negligible mass. And finally, I'm not sure if you had time to do this in your course. I know I spent very little time on this, and that is the model that you'll be learning about in your next course, if you take some more chemistry, you should, is the wave mechanical model. The wave mechanical model was used to explain the spectra of elements with multi-electron, more than one electron atoms. The Bohr model was really developed by in explaining the spectrum of hydrogen, which has only one electron. So for multi-electron atoms, they came up with this wave mechanical model, and maybe if you took an institute class or an honors class or something like that, they may have had time to cover this, where they spoke about S, P, D, and F, orbitals, not orbits. All right, and we can think of an orbital as the region of space, 3D space, around the nucleus of an atom, where an electron can most probably, he is probably now, there's a 90% probability of finding an electron in this region. It's also known as an electron cloud. All right? So this happens to be an illustration here of an S orbital. The orbitals they differ in shapes, they differ in sizes. All right, they differ in 4 different ways. But the important thing to know here is what an orbital is. And what I'm trying to convey here is just that as a region of space around the nucleus of an atom. So these are your axes here, which are the x-axis, the y, and the z, three-dimensional. Think of the nucleus as central. And maybe another way of thinking of this is, how to generate this picture is, if you had a high-speed camera that could actually take a picture of electrons, which you can, but let's pretend you can. What we're saying is that if you could take a picture in this instant, there's the electron, and then if you continue to take pictures of that electron over time, and you put all those pictures together, if it's an s orbital, what you find is that 90% of the time, that electron will be found in a region which is spherically shaped, and if you put it all together, you get that picture. All right, so it's really a matter of probability. And you'll talk more about this, certainly out of the scope of the Regents in your next course. All right, well, we're pretty much done with atomic structure. You can take a break now if you want, or we can move on to some questions. And what I suggest with the questions is, once you've gone through the notes and you're confident in the notes, to see if you really have mastered them, is try doing the questions on your own. And then we'll do the questions together. All right, so you should download the questions, print them out, try doing them on your own. And the questions, as you'll see, and I'll point this out to you in the next page, they're very small, but you can notice towards the bottom of the page the answers are there. So you can test yourself. And then if you're having issues with that, then wait for my explanation. Again, the more questions you do, the multiple choice, the greater your chances of doing real well on the Regents. All right, let's turn to that. Whatever you like. We'll meet you there.